Building a cathedral roof in a cold climate can be a challenging process. You have to have good insulation, good thermal performance. You have to have good moisture management in terms of keeping the humidity that's generated indoors in wintertime out of that roof assembly. And you have to have good ventilation on top of that roof deck to prevent ice dams. So in this demonstration project here, we've got a couple of different ways one can approach framing a cathedral ceiling that will perform well in a cold climate. We'll be insulating this roof with a blown-in fiberglass, mostly because that's what we had available to us on short notice. Quite frankly, either a blown-in dense pack fiberglass or a blown-in dense pack cellulose would be an excellent choice for a cathedral roof system like the one we've got right here. What's really important is some of the decisions we have to make when we're stick framing this roof system to make sure that it will perform well in a cold climate. It has to be very well insulated, it has to be very well ventilated on top so we don't get ice dams, and we have to have good moisture control on the inside. We need to keep water vapor out of that roof system in wintertime. So let's take a look, let's take a step back and review some of the decisions we've made in the framing stages to ensure that this roof system will perform well. We've now completed all of our roof framing to the point we're ready to start putting roof sheathing down. And this would be a good point to stop and talk about roof ventilation. Now, the International Residential Code requires a minimum of a 1-inch airspace between the top of your insulation and the underside of your plywood or your OSB roofing. Now, the reason for this is twofold. One is we don't want the insulation contacting our roof plywood, because then you could have heat losses through the roof that will cause the snow on top to melt, which would create an ice dam. The other line of reasoning for this ventilated airspace on top of our roof is that if we get any water vapor or moisture in here in wintertime from our heated enclosure due to air leaks, then you've got a drying path via that vent space upwards through the roof and out. For a cathedral ceiling like this, a cardboard baffle is a common option. The baffle fits in between the eye joists and staples up against the flanges. The nice thing is it gives us a nice fat 1.5 inch airspace between our insulation and our roof deck. Cardboard baffles aren't the only option. The construction industry also makes plastic baffles, polystyrene or PVC for instance, and in wet climates those may be a better choice. They've got better durability if you've got any chance that you might have long-term exposure to moisture or wind-driven rain. Here we are looking at a section of cardboard baffle from above. You can see the eye joist flange thickness is 1.5 inches. It's nice and clear, but down here we do have a bit of a problem. Structurally, this blocking is working out great because it's tied into the rafters, but it does create an air passageway problem because it effectively blocks off the lower end of the roof where we're counting on that fresh air to get in. So that is something you'll have to consider in advance to make sure you're getting a good structural connection and a way to ventilate this eave. Some folks like to use foam board, and this is where I would be very cautious. Unlike baffles, which tend to go up in sections and have spaces between them and not be perfect, if you take foam board and friction fit it in here, there is very little, if any, air movement around this foam board, and it's impermeable enough that if you got enough water vapor into this roof in wintertime due to an air leak of some type, you could have a serious moisture problem and things would be slow in drying out and you may end up with some mold. If you do a really good job with the vapor retarder inside here, you may not have a moisture problem. But to me, it's just cheap insurance to have an optimal drying path up and outwards into that vent space. On this particular roof, we've chosen to frame a 4-foot overhang, and typically the way this is done is you run a lookout, a 2x6 in this case, into the roof 4 feet. Structurally, that works out really well, but it does create some challenges for roof ventilation, because now, when our plywood sits on here, we've blocked off at every lookout point airflow for our ventilation up the roof. So for this particular roof, we're going to do something a little different in terms of ventilation. Rather than venting our roof on the inside in the rafter bays using baffles to create a 1.5-inch airspace, we've done a different approach here. What we've done is nailed 2x4s on the flat over a layer of Tyvek to create our airspace. Because the framing over the lookout area in particular is pretty complex, it would be very hard to vent, and so this here allows us to create a dedicated, easy to vent airspace all across that roof. We're counting on our Tyvek here to keep our insulation out of our vent space, and since we're using blown-in insulation, it's going to be really important that there's a close row of staples running along the bottom here so the insulation can't lift this Tyvek as it's getting blown in from above. Also, the tighter and flatter you can get this Tyvek on top of the roof, the less bulging there will be up into the vent space. This isn't something you'd want to do in windy weather, and the more manpower you have for this operation, the better, because you can get different people pulling from different directions, making sure it's nice and flat. The only other pointer I'd like to make is if you've got a big roof with long rafters, you may want to put a spreader on layout across the top of that roof or across the middle of those rafters to make sure they're on layout, because once that Tyvek is stapled to the rafters, there won't be any adjusting them later. Now that we've got one row of sheathing on, we can see that we've got a nice 1.5-inch airspace in every rafter bay. We have changed the way this roof system works structurally by nailing these 2x4s on the flat and then nailing our sheathing on here. And this is something to be aware of. If you're working with an engineer, a code official, if you're in a seismic region where this may matter, or if you're in a wind region where this may matter, be sure that the attachment of this 2x4 and the sheathing meets your local code and engineering requirements. There's another detail I'd like to point out, and that's our rafters and blocking over our bearing wall. And there's no one right way to do this. There's many different ways one can frame this connection. In our case, I've actually cut my studs to the roof pitch. It's a 6/12, and I've pitched my plate as well. This allows me to nail my eye joists directly into the double top plate, as well as my structural blocking goes in perpendicular to my double top plate. And this has a couple of advantages. If I'm insulating with fiberglass batts, now I've got a square edge. I can just butt my batts against that. I don't have to actually cut my roof pitch on the edge of the batt. That rarely works out very well. In addition, having the blocking pitched out like this maximizes the amount of insulation I could get over the top of this wall. When framing with eye joists and rafters, it's pretty common to have an airspace between the blocking and the rafter. And that can cause some problems. For one, if you're blowing in insulation, this right here is a place where that insulation can come out and it can plug up your soffit vent. That will affect your roof ventilation performance. It's also an air infiltration point. So if you've got a lighter density insulation, fiberglass batts for instance, the last thing you want is wind washing and cold air finding its way in there. So this should be air sealed, and depending on how you're doing this, you can staple on blocks, or you could put in spray foam after you've insulated with fiberglass batts, and that would make a nice seal there too. I've applied the poly, sealed it all the way around, so it's now a very good air and vapor barrier. My plan here is to blow in insulation from above, and since I am stuck with a 12-inch rafter bay, whether I'm using blown-in dense pack cellulose or fiberglass, I can only get so much insulation into that 12-inch airspace. Since I personally want a little bit of a higher R value, I will be adding 2 inches of foil-faced EPS foam board to the entire underside of this ceiling. So whether I'm using a blown-in dense pack fiberglass or cellulose, when I combine that with the 2 inches of EPS foil-faced foam board here, I'm looking at a total nominal roof R value of somewhere around 55 or slightly higher. One nice thing I want to point out here is when your poly air and vapor retarder is sealed to your ceiling rather than to your beam, your foam board can go up here nice and flat. You can jam it against the beam and you don't have to worry about disrupting the poly, tearing any staples. You've got all the room in the world to do so. So we've held our strapping up with structural screws, and we're counting on both this 25 psi foam and the strapping to provide the support for that blown-in insulation that's going in from above. And we're planning on that insulation being about 1.8 to 2 pounds a cubic foot, and I think this should be pretty adequate as far as a means of support for that insulation. Because we have blowing equipment available to us, we've opted to use blown-in insulation in this roof system. And when you look at an I-joist like this, they can be difficult to insulate with fiberglass batt insulation. It takes extra time to get good detailing around the different contours in the I-joist, whereas a blown-in insulation will fill this cavity completely and you'll get a form fit around the different profiles in the joist. Regarding our roof system, we've also got large overhangs where we had to frame lookouts that have made for some pretty complicated framing inside our insulated roof envelope that would be very difficult to insulate with fiberglass batts. As we have complex framing complexities, we felt it would be a better choice to use a blown-in product. And to demonstrate, we will be insulating this roof, one half of it with blown-in insulation from above and one half of it with blown-in insulation from below. The theory being that there are advantages to both approaches depending on weather, time frame, height of building, and what's more readily accessible. We run the hose all the way down to the bottom and then start backing it up as we feel resistance. In my case, the Attic Cat blowing machine has a 2.5-inch hose, so I was able to take a straight section from a shop vac and hose clamp it onto the end. I like this because I get a lot better feel for where I'm at, and if I need to pack things in a little bit or work through the insulation, the end of this guy is rigid enough to allow me to do so and feel that. When you're putting on your Tyvek, it's very critical that that Tyvek is on fairly tight, because the denser that insulation is when it goes in, the more it wants to bulge the Tyvek, and we want to be sure to keep our airspace, our vent space open here. If you find that the Tyvek is too loose, before you blow the insulation in, you could slide in a piece of 1.5 or 2-inch foam right down the center of your rafter bay. That would create a space there and help keep that airspace open. If the Tyvek's tight, you shouldn't have any problems. Another point I want to make is when you're putting the Tyvek on, it should come all the way to the peak. The idea is then all you have to do is cut a small hole here and insert the hose. If you had an airspace here that was all the way open because the Tyvek was short, you'd have a lot of insulation blowing back out at you, which would create a mess and make it hard to work with. We are blowing in, I would say, probably at about somewhere between 1.8 and 2 pounds a cubic foot density. That's strictly based on the bag count and the amount of insulation weight-wise we have in every bag, so it's pretty easy to calculate. And that would give us an R value of slightly over 4 per inch. That's pretty good, and it also helps because the denser this product is, the more resistant it is to airflow, and at R4 per inch, 1.8 pounds a cubic foot, it's going to be highly resistant to airflow. But you can also tell by feel, this is nice and firm. And I can feel the hose when I'm pumping the insulation in and get a pretty good idea of how I'm doing as I'm moving along. So here we're at the last 4 feet of our roof, of our heated roof section. As you can see, we've got 2x6 lookouts, and those lookouts travel all the way back to here to give us support for that roof overhang. So this here has a lot of complex framing, and this is where a blown-in insulation really shines, because you can still take, as long as you have room to go all the way to the bottom of the bay, you can still fill all those sections in between every lookout, because there's enough pressure here that that insulation will fill as you back the hose out. That's all she wrote there. On this half of our roof, rather than blowing in from above, we've chosen to blow in from underneath. We're using the same blown-in fiberglass insulation, but in order to blow from underneath, we've stapled on a non-woven polypropylene mesh. It is air permeable, so it does relieve pressure as you're filling the bays. There's many different ways to staple on this mesh. I prefer to actually get the mesh on tight, just like you would put on 6mm poly across the ceiling, and then hem in and staple just along the inside edge. And that reduces the chances of getting any insulation on this edge here. The stapler I'm using is actually a variable rate select fire stapler, and it travels along and runs a nice even row of staples. It does take some getting used to, but the idea is once you get the hang of it, you're stapling at about 1-inch intervals all the way along. Here we're filling in the area where we have our lookouts framed, so there's a lot of complexity here. So the insulation is filling both bays, and then I'll just move up as I go. I can tell I've got a really good amount of dense pack in here. No matter what insulation you're using, whether it's a blown-in fiberglass or a blown-in cellulose, it's well worth checking your density and seeing how much insulation you're getting into the first few bays, and then checking as you're going along. Every insulation manufacturer will provide specs based on the weight of a bag of insulation, what your coverage is and what your R value is at a given density. And the calculations are provided by the manufacturer. They're pretty straightforward, but the nice thing is it may take a little while to get a feel for the process, and so if you can stop and check periodically, you'll get a really good idea of how that insulation's going in and how you're doing. So here we're looking at the half of the roof that we insulated from above, and I found in this particular job it was significantly easier insulating from above than it was from below. Mostly just easier on my body because I didn't have to manipulate the hose from underneath. I could work right along the ridge in comfort. One thing we would do differently next time strapping the ceiling like this is we would split the strapping right on a joint in the foam to have full support here. And that's an important issue. Remember, if you're blowing insulation into a roof from above, the last thing you want is the weight of that insulation and all that air pressure as you're packing that insulation into every bay to tear that poly, to tear the staples loose. And so you need to have really good support. In this case, we used 2 inches of 25 psi EPS foam and strapped it every 2 feet on center, and that proved to be quite adequate. We were curious though, and so we cut away a section of foam, and we saw here where we had stapled, everything was still nice and snug. So based on this anecdotal observation, we feel pretty comfortable that at least with a 12-inch I-joist bay and this fiberglass blown in at somewhere around 1.8 pounds a cubic foot, that this weight of this insulation doesn't stress the poly. The critical thing, as I said, is you need to have continuous support for this plastic because the weight of the insulation could tear it loose. If you find yourself in a situation where you are concerned that the standard 6 mil poly on the ceiling can't resist pressure of insulation going against it, another option might be a reinforced poly such as this Durascrim. It's also 6 mil. It has a very low perm rating comparable to that of the standard 6 mil poly, but the fiber reinforcing makes it a lot stronger and more resistant to tearing. That doesn't mean the staples won't pull out under pressure, but the material itself is a lot tougher and it costs a little bit more, but in the grand scheme of things, it might be another choice if you have concerns. So now we're looking at the half of the roof that we netted and blew the insulation in from below. And I'd say overall the process was very smooth. We had a very good uniform density, and our target density was about 1.8 pounds a cubic foot. As per manufacturer specifications for this blown-in fiberglass, that is supposed to yield an R value of 4 to 4.3 per inch. And one thing we did notice though is in between the rafter bays, that netting was sagging under the weight of the insulation anywhere from 1 to 2 inches. And so when I started putting on my polyethylene sheeting vapor retarder, I went along and pushed up the insulation in each bay in an attempt to get my poly to lay flatter. And that worked out okay, but it took a little bit of extra effort. And I've also noticed that even with the poly up, there is still some sag in each bay here between the rafters. So I'm curious to see how the drywall will do, and we'll put up a sheet, see what happens. So now we've got our first sheet of drywall up, and I will say it was more difficult to put this drywall on the ceiling than it normally would be. We still ended up having to push the insulation up in every bay before the drywall went on, and it took more screws per row just to be able to suck that drywall tight to every rafter edge. And so we actually physically had to push a little harder and make sure that everything went tight. And as we went along, we also ran a straight edge along to make sure that we didn't have any bulges, and so that everything went up. We are following the U.S. Gypsum Corporation's Gypsum Construction Handbook. The U.S. Gypsum Corporation specifies that for framing 2 foot on center using 5/8 drywall, this drywall can support 2.2 up to 2.2 pounds per square foot of insulation. Since we're installed here at about 1.8 pounds per square foot, we're well within spec. But we were still fighting those bulges. So my impression here is, yes, you can do a good job with this, but it will take extra effort. And so if you're going to be hiring a drywall installer, they'll need to be aware that they'll have to take extra time to make sure that these sheets go up nice and tight and flat, and that you won't have any nail pops later. Now, as an alternative, I would consider strapping this ceiling. I think it might actually be easier to strap the ceiling with 2x4s and then apply the drywall. So we'll put some runs of strapping on here and make a couple more observations on the process. So now that we've got our ceiling strapped, in this case we used 2x4s on the flat, 2 foot on center. I can say the process went very easily. And the nice thing is the 2x4s are thick enough and stiff enough that they bridge the distance, 2 foot on center, between the rafters just fine, and we're able to push that insulation up no problem. So the 2x4s are on nice and straight, and that means when we put the drywall on, it'll be on nice and straight too. There are a couple of other advantages to strapping a ceiling with 2x4s. For one, you're minimizing the number of fastener penetrations because now your drywall is screwed to your strapping, so you've got a lot less holes in your ceiling air and vapor barrier. In addition, if you need to run wiring in your ceiling, this channel here between the straps provides a wiring chase, and at 1.5 inches thick, the 2x4s will allow you to mount shallow electrical boxes. So you can mount smoke alarms, CO detectors, track lights, any kind of electrical systems like that, and you never have to cut into your vapor barrier. You've got a nice airtight seal up here, and all of your other work can be done down below. If you're going to be strapping a ceiling like this with 2x4s over foam, you've got a variety of options. I prefer to use screws, and structural screws in particular, but I'm going to go through a couple of different types of screws you might come across and list the pros or the cons of each. My least favorite choice would be a drywall screw. It's going to be by far the cheapest, but remember, it has to go through unsupported 2 inches of foam board, and it has to carry the weight of the insulation in the ceiling and the weight of the drywall, and I'm not convinced a screw like this would be up to the task. Another screw that can work, but I would also be cautious of, is a self-tapping screw for metal. It is a structural screw. It's got a nice flat pan head on it, but the threads are so fine that you're going to have a lot of resistance as you're trying to drive that screw through the furring strip, so it'll be a lot more work. In terms of holding power, a landscape screw like this with a hex head can work, but the hex head will stay proud unless you pre-drill and recess every point you're going to have one of these screws. I think by far the best choice would be a structural screw designed for wood with a pan head like this that will recess itself when it drives into the furring. Remember, you're using an impact drill, you're working overhead, you want this process to have as least resistance and go as fast as possible. If you have any questions or concerns about what this furring can carry in terms of weight, consult a structural engineer. So now we've finished insulating both halves of our roof system, and though our approaches were radically different since we insulated one side from above and we insulated the other side from below, the end result was still the same, as you can see. Let's take a look at the R value by the numbers and see what we've got here. A 12-inch I-joist insulated with Attic Cat fiberglass insulation, dense packed to about 1.8 pounds a cubic foot, is rated by the manufacturer to give us an R value of about 52. Then 25 PSI R-Tech EPS foam at 2 inches thick yields an R value of about 9. And then the EPS foam board has a radiant quality barrier on the bottom, so we can slow down radiant losses. That gives us another 2 points or so of R value. So in doing this roof system like this, we've got a total roof R value of over 60, which is pretty good. That's not to say there aren't other ways, many other ways you could insulate a cathedral like this, but hopefully by pursuing this project start to finish, we've just given a couple of options if you're looking at doing a roof system of this type.